Okay, this is Thermodynamics, Chapter 10, and a few sections of Chapter 11. So let's start with defining temperature. We all know that temperature is a measure of how hot or how cold something is, but what I want you to realize is temperature is a measure of the average kinetic energy of the molecules that make up the object. That's called the heat energy. So when you think about temperature, I want you to visualize molecules bouncing around, they're moving around, they've got kinetic energy, and all of those molecules together give the object its temperature, which is its measure of its kinetic energy, because if they're bouncing around more rapidly, there's more kinetic energy, it's a hotter object, it has more heat energy. Temperature also determines which way heat will flow. An object that has more temperature has more kinetic energy, depending on the mass. Now I'm talking about two objects that have the same mass. If they have the same mass, the one that is hotter has more kinetic energy, and so that's the one that will lose energy to a cooler object, because heat will always flow from hot to cold. From hot to cold. Now when objects are at the same temperature, we call that thermal equilibrium. Some people say that a thermometer actually doesn't measure anything but its own temperature, because it must become in thermal equilibrium with your body, and when that happens it's actually measuring its own temperature, not just the temperature of you. But that is how a thermometer works. Heat flows from hot to cold until the two objects are in thermal equilibrium and heat is no longer being transferred, and that's the temperature that you read off the thermometer, which is equal to your temperature. That's also why it takes a little while. You don't just put the thermometer underneath your tongue and then take it out and see what it reads. Now there are those that go in your ear and different things that are instant read thermometers, but regular thermometers, you need to allow the heat to equalize between the two, and that takes a little bit of time. Now this objects being at the same temperature, called thermal equilibrium, that's sometimes referred to as the zeroth law of thermodynamics. There's three laws: zeroth, first, and second. Okay, heat flow is given in formulas by the letter Q. Heat is energy, and that energy flows from one object to another if the two are at different temperatures. So since heat is energy, it's measured in joules, just like we have always done. When we talked about kinetic energy, when we talked about potential energy, we measured those in joules. But before we knew that heat was really a form of energy, because energy has so many different forms, before we knew that, we measured it in calories, and we do still follow this convention. So we measure heat in joules or in calories. Think about how many calories you have to, quote, burn off when you eat a candy bar. You're converting those calories to heat energy. Now, heat flow between two objects that are placed in contact is determined by three things. The temperature difference. Heat will always flow from the hot object to the cold object. The masses of the object make a difference too in the amount of heat transfer. And then the specific heat is given in formulas as the letter C, specific heat. And I like to add the word capacity onto the end of that. Specific heat capacity. It depends on the material, and specific heat capacity is how much heat energy that object or material can absorb before it changes its temperature. So our formula then, our working formula for heat flow is Q is equal to mc delta T, which I often write Q is equal to Cm delta T in an equation finder form, where Q is our heat energy, and again heat energy is measured in joules or calories. Delta T or triangle T, that's our change of temperature. M stands for the mass, and mass is typically measured in kilograms, occasionally measured in grams. And then C, that specific heat capacity, and that's a number. Now, 1 is the specific heat capacity of water. And so that means water takes 1 calorie of heat energy to change 1 gram by 1 degree Celsius. And we could scale that up. We could say that water takes 1 kilocalorie of heat energy to change 1 kilogram of water by 1 degree Celsius. And we could do the same thing with BTUs. It's how much energy it takes to change the temperature of that material by 1 degree Celsius. So that's specific heat capacity. Water is really high. Water has a specific heat capacity of 1. Think about that. That's why it takes a couple days for the swimming pool to heat up after it's been filled. You don't go swimming the first day they fill the pool. It's still really cold. Water has a high specific heat capacity. It takes a lot of heat before water changes its temperature by 1 degree. That's also why we use water to cool hot objects. Water can absorb a lot of heat energy without changing its temperature very much. For comparison, aluminum has a specific heat capacity 0.22. Very, very low. Aluminum changes its temperature rather quickly. So that's specific heat capacity. So think about the Arctic ice cap and a cup of coffee. The Arctic ice cap has more or less or the same total energy as a cup of coffee, and its temperature is more or less or the same as a cup of coffee. So I want you to pause this presentation, think about it, and have an answer in mind, and then hit play again. Okay, you're back. I hope you realize that the temperature of the Arctic ice cap is colder. So the Arctic ice cap is colder than the hot coffee. But what you may not realize is the Arctic has more energy than the cup of coffee. Let me show you why. Here's my cup of coffee. I got 5 molecules of coffee, so there they are, 5 molecules. But they're really hot, so they've got 100 energy units for every molecule. So that's 500 energy units. Really hot coffee, so lots of energy per molecule. But now I've got my great Arctic ice cap, and I've got 10,000 molecules in this Arctic ice cap, but they're really cold, so there's only 1 energy unit per molecule. But that means I still have 10,000 energy units in this Arctic ice cap. So the Arctic ice cap has more total energy than the cup of coffee, and its temperature is less than the cup of coffee. So that was number 4. Okay, let's go on. Specific heat capacity we've talked about before. I just want you to realize objects with a high specific heat absorb heat slowly, and the rate that they absorb it is also the rate that they release it. And so the specific heat capacity is really a measure of how easy or hard it is to change a material's temperature. The specific heat of water that we will be using is 1 calorie per gram degree Celsius for water. So that's a constant that you need to know. Okay, specific gravity is not specific heat. Specific gravity is a density comparison, and we're not going to deal with that. So I just want you to know that's not what we're talking about. Okay, so let's do some of the math. This is an example of a Q equals CM delta T problem. This happens when an object changes temperature. When an object changes temperature. Right? If we've got delta T in the formula, the object must be changing temperature. So, I'm going to write this in our equation finder form. How many calories of heat are given off by 500 grams of aluminum when it cools from 650 to 450 degrees Celsius if the specific heat of aluminum is 0.22 calories per gram degree Celsius? So here's our specific heat, 0.22 calories per gram degree Celsius. And the mass that we were given, 500 grams, and the temperature difference, 650 minus 450 is 200, so 200 times 500 times 0.22 yields an amount of heat energy of 22,000, and that would be units of calories. That's the unit that the specific heat value was given in, so that will be the unit of the final answer. So, 22,000 calories of heat are given off. A glass of water cools from 30 to 10 degrees Celsius. How much heat has left the water? This is the same type of problem. We've got a change of temperature, and we'd like to know how much heat has left. And we cooled by 20 degrees Celsius. That's 30 to 10 degrees Celsius. And I forgot to tell you the mass. Let's say this is a 30-gram mass glass of water. So 30 grams. My fault. I'm sorry there. So 30 grams of water, not very much. Probably, let's make that 330. 330 grams of water. And then we need to know the specific heat. And the specific heat of water is 1 calorie per gram degree Celsius. So all we end up having to do is taking 1 times 330 times 20, and that gives us 6,600 calories has left that glass of water. 6,600 calories. Okay, I want you to remember, if the specific heat is not given, it's 1 in terms of calories. Now the simulation that you'll be dealing with today uses a different value because it's specified in different units. But for your homework, we're going to use 1. Okay, phase changes and latent heat. When an object goes through a change of phase, heat has to be added or removed, but the temperature does not change. Instead, the state of matter changes. So what I'm saying is if I've got ice water and I add heat to it to melt the ice, while I'm adding that heat, the temperature of the water is not changing. It's remaining constant. And I can show you this when I get back to class. There's a lab day demonstration that I do where I will take a beaker of water, place it on a hot plate, and I'll have ice water in the beaker, so I'll crush up some ice and add to it. I'll continually add heat, but you'll see that the temperature doesn't change until the water melts. I'm sorry, until the ice melts. Okay, the amount of heat needed per unit of mass to produce this phase change is called latent heat. That's how much heat it takes to change phase. That's called latent heat. So we've got 2 points we need to talk about then. The latent heat of fusion is when water converts to ice and vice versa. The latent heat of fusion has to think of fusion and think of a solid. Ice is a solid. So the latent heat of fusion is how much energy it takes to change state between ice and water. And so if we are changing from ice to water, we're adding heat, and if we are changing from water to ice, we're removing heat. But in both cases, the amount of heat it takes is the same value. And for water, that's 80 calories per gram. 80 calories per gram. The latent heat of vaporization is the amount of heat energy it takes to turn a gram of water into steam. So think of vaporization, that's something that's being vaporized, so that water can be vaporized and turned into steam, or that steam can be condensed back to water. If we add heat to hot water, 100 degrees Celsius water, we can turn it into steam, and if we remove heat from steam, we can turn it into water. And again, the amount of energy that requires is the same in both cases, and it's 540 calories per gram to change water, 100 degrees Celsius water, to 100 degrees Celsius steam. Okay, so changing phase. The formula is Q equals ml. Notice that we're missing specific heat and we are missing change of temperature. This is the formula for changing phase. And in an equation finder form, it would look like this. Q is equal to m times L, where L is the latent heat of either fusion or vaporization, depending on what's happening. And then, of course, m is the mass. Now remember, when we are changing phase, the material will not change temperature. So let's look at an example. What heat is required to melt 50 grams of ice? So my 2 working formulas, Q equals Cm delta T and Q equals ml. Since I'm not changing temperature because I am melting ice, I want the latent heat formula, Q equals M times L. So how much heat, how much Q is required to melt 50 grams of ice? Well, if I'm melting, that's latent heat of fusion, which was 80 calories per gram. So 80 times 50 is 4,000. It takes 4,000 calories to melt 50 grams of ice. What heat is required to turn 20 grams of water to steam? This is the same formula, but now we're dealing with turning this into steam with this 20 grams of water. So that takes 540 calories for every gram. That's the latent heat of vaporization. So when I take 20 times 540, I get 10,800 calories to turn 20 grams of water into steam. So I'll ask you questions like this, and I call these follow the energy questions. You need to think about what's happening to the energy and think about where the energy is going. So a farmer in Florida learns that a rare frost is expected overnight. His fruit are less likely to freeze and be ruined if they are wet, if they are dry, or it makes no difference. So again, pause this presentation and make your selection. Okay, you're back. So I want to think about what happens to this fruit if they are wet. So if I've got fruit and they are wet and it's cold outside, it's near freezing, energy is going to be leaving my fruit. Now if I cover my fruit with a thin layer of water, energy is going to be leaving the water instead of leaving my fruit. So if I cover this fruit with a thin layer of water, it takes 80 calories to change every gram of water to ice. So 80 calories per gram of water will protect my fruit. My fruit are less likely to freeze if they're wet because the energy has to come from somewhere, and it's coming from the water instead of from my fruit. So his fruit are less likely to freeze and be ruined if they're wet. Your grandma knew this. The same thing happens with flowers in the springtime. Your daffodils or your tulips are up and there's going to be a hard frost. So you go out and you sprinkle them with water, and they don't freeze, so they still bloom. Because if they get nipped, they're not going to bloom. And so that's the old grandma's way for keeping your flowers blooming, your tulips and your daffodils, in the early spring. Sometimes this takes a little while to get a handle on. There's a couple questions on tomorrow's self-quiz that address this as well. Okay, the first law of thermodynamics states that doing work or adding heat transfers energy and changes the internal energy of the object. We all know this. If we put a flame underneath, or a hot plate underneath a glass of ice water, we are adding heat to that, and that will change the internal energy. It will heat up. Its temperature will rise after all the ice is melted. So internal energy is really an interplay between the heat that's added and the work that's done. We do this all the time with the steam engine or internal combustion engine. It's an interplay of heat and work. We create a source of heat energy, and we use some of that heat energy to do mechanical work. And so what I want you to realize is then when we have a gas that is expanding. So I'm just going to talk about balloons. I've got a balloon. It's got 10 joules of internal energy. The balloon pushes on the air around it, and the balloon expands. Now you all know an expanding gas cools. So the internal energy of this system has to go down. Let's say the balloon does 2 joules of work pushing the air out of the way as the balloon expands. Well, this balloon now has 8 joules of internal energy. We've lost or transferred out 2 joules of energy. Now, let's talk about the balloon again. 10 joules of internal energy, but I'm going to push on this balloon and I'm going to compress it smaller than it was before. And I'm going to push on it with a work value of 2 joules. So 2 joules plus the 10 joules I had before means I now have 12 joules of energy. We're compressing the gas, we're doing work on it, we are increasing its internal energy. So the energy of the system increases. So there's always an interplay there between work and heat energy. And what I want you to realize, either heat can be added or removed, and that will change the temperature, the internal temperature. Work can be done on the object, compressing it, or by the object, allowing it to expand, which basically deals with the volume of the object. So if Q is greater than 0, I added heat. If Q is less than 0, I removed heat. If W is greater than 0, then my gas did work expanding, and if W is less than 0, then I compressed my gas and made it smaller. Okay, so let's look at the types of problems I'll ask you. What is the change in internal energy if 900 joules of heat is added to a system that does 400 joules of work? I always want you to think about the amount of heat and the amount of work. So, what is the change in internal energy if 900 joules of heat is added? Well, that means I'm up by 900 because of heat. And then the system does 400 joules of work. So the system is expanding. The gas is expanding. It's doing work on its surroundings. So if the gas is expanding, and expanding gas cools, we're losing 400 joules of energy. So our change of internal energy then is 500 joules. Let's look at the next one. What is the change in internal energy if 500 joules of work is done on a system? So I did work on the system. Oh, my fault there. Sorry about that. 500 joules of work is done on the system. I need to put that on the work side. 500 joules of work done on the system. That's like compressing it. And 300 joules of heat was added. So the heat's being added, not removed. Our change of internal energy is 800 joules. Okay, let's keep going. A gas is confined in a cylinder with a movable piston. You add 100 joules of heat to the gas. At the same time, the gas expands, doing 200 joules of work on the piston. What happens to the internal energy of the gas? Go ahead and pause this presentation and then come back when you have an answer. Okay, this is an interplay of heat and work again. And so I add 100 joules of heat, so I must be up by 100. The gas expands, and expanding gas cools, so the gas is losing 200 joules of energy as the gas pushes on the surroundings. Energy is transferred out of my system. So I am down by 100 joules of energy. The total internal energy of the gas has declined. Next question. Assuming no phase change occurred in the previous question, what happened to the temperature of the gas? Again, pause this presentation while you make your selection. Okay, you're back. If I was down by 100 joules for internal energy on the last slide, then if my energy is down, the average kinetic energy per molecule is down. So the temperature must be decreasing, because temperature is a measure of the average kinetic energy, and I have less energy than I did before. Okay, that is the end of this slideshow. Let me know if you have any questions.